Okay, I am restarted recording again, and got about one more minute here. And then I'll give you a quick introduction here, and then you can start.
Okay, sounds good.
Hi, everybody. Welcome back from your break. It was a quick break, but we're going to get, we got Whittam Reeve, next speaker, contributing editor for the SARA Journal, Radio Astronomy. He obtained BS and MS degrees in electrical engineering at University of Alaska Fairbanks. He worked as a professional engineer and engineering firm owner operator in the airline and telecommunications industries for more than 40 years, and now manufactures electronic equipment used in radio astronomy. He's lived in Anchorage, Alaska his entire life. Okay, Whittam, go ahead.
All right, thanks, Rich. I'm gonna try to advance my slides here, and for some reason, there we go. My talk today is important celestial radio sources. And Rich, thanks for asking me to give this presentation. I put this together about 10 years ago, and when I first started getting going in radio astronomy, and I was thinking about building a reflector antenna at the time. So I figured, well, I better investigate the sources, what sources out there, determine what it would take to detect it. Actually, I ended up not building a reflector antenna, and instead built 3 observatories around Alaska, one in Anchorage, one in Gakona where the HARP site is, and one in Coho, south of Anchorage on the Kenai Peninsula. So what I'm doing now is solar radio, Jupiter radio, radio propagation, meteor trail, reflections, and magnetism. So rather than actually going into the important celestial radio sources, I'm doing a lot of other stuff. But it turns out that I wrote this 10 years ago, and I think I published it in the SARA Journal a long time ago. And in 2014, I actually posted the article on my website, where it lay dormant for several years. But in the last couple of years, I've been getting emails from people saying, thank you for doing that. And so that kind of made me feel good, because I didn't realize that people actually read any of my stuff. So I've got it, the article has a table in it, which I'll show you in just a minute. And you'll notice that the most current epoch is about 20 years ago. So almost all of them are observations that were made in the year 2000. And there's actually a couple of them in there that were made in 1950. And over time, the flux densities of some objects have changed. In particular, the Cassiopeia A supernova remnant has decreased in flux density over the years. And I give you a couple references there where you can see what work's been done on that. And there's very possibly others that are shown on my list that are the flux densities are not current by any stretch of the imagination. So this, I limited my, the research that I did to spectral flux densities greater than 40 Jansky. Not that I thought that I could observe down to power levels that small. It's just that I arbitrarily chose that as a breaking point. And you'll notice that up here at the very top, the most powerful source at the time was the supernova remnant Cassiopeia A. And I also noticed that the frequency is 1420. That's a very popular observing frequency because that's your neutral hydrogen. There's a couple others that are at other frequencies. And so these, the flux densities that you're seeing here were made at that frequency. And as I mentioned just a minute ago, Cassiopeia A is much lower than this now. I think it's down in the neighborhood of maybe 900 Janskis, something like that. So it would be dropped. It would drop down down to here somewhere. But in any case, I've got these broken out by object name, and these refer to the catalog that they're listed in, and then their coordinates in right ascension and declination, when the measurement was made, the actual density and the frequency. And a lot of these specific radio objects shown on the left column have other names as well, or they may be nearby some easily recognized object. So I've shown those over here in the far right column. And this is just an extension of the list that's in that article. And this is between 14 and 40 Jansky. And now you're going to have a pretty good sized array or a really large dish antenna to be seeing things this small. But I've got them listed there anyway, in case you want to take up the challenge.
Hey, Whit, Wolfgang on the thing says his latest measurement about 2 years ago of Cas A is 1550 Janskis.
1650?
1550.
1550, okay. So
that's not too bad.
Yeah, it's still definitely up here at the top, but it's probably not the very top right now. So yeah, thanks for that, Wolfgang. Here's the end of the list, and it looks like I went down to 10 Janskis here, and again, you're going to have a pretty good sized system to be observing that. Now, having using equatorial coordinates, right ascension and declination never made a lot of sense to me. I mean, I understand the principles and all that, and I can figure it out. But all my working life, I used elevation and azimuth. So I wanted to kind of get an idea of, okay, where in the sky are these objects, these radio objects that I've got listed in that table? So I made this chart or this map, and the underlying map, the contours that you see here, came from an ITUR document, P.372. And the map is, the contour on this map are actually at 408 megahertz. Yet the objects that I'm showing here, for example, here's Cassiopeia A, the table shows that at 1420 megahertz. So don't get confused by the contours. It's just that I wanted to have some visual reference so that I could look up in the sky and say, oh yeah, there's Orion. And even though I already know where the constellation is, this map here should help you a little bit trying to figure out where in the sky these things are. And here's the ecliptic, this dashed line here, S-shaped line. And of course, this is the Milky Way. This is our galaxy, the equatorial plane, or the plane of the galaxy, this large, dense S-shaped thing here. Now that map that you just looked at is a composite of 4 individual quadrant maps, which I'll show in a minute. And these are I took these straight from the ITUR recommendation and scanned them, and then brought them into a drafting program. I use Visio for that, which I don't recommend anymore. But I brought it into Visio and then put the colored ovals on it. The annotations on that map only show locations or sources with flux densities that's greater than 40 Jansky. Here's one of the quadrants here. And if you go back and look at the map, you'll notice that the declination is shown here on the left-hand scale with 0 in the middle and plus 90 and up, and then minus 90 down. And then the right ascension is 0 to 24, but it's kind of quirky. The original maps go from 12 on the far right, lower right corner, to 24 in the middle, and then go from 0 to 12 over on the left-hand side. So it's not like you're reading a continuous 0 to 24. It's kind of split down the middle. And the quadrants are basically the same way. 0 starting on the right to 12 hours on the left. And this is the upper left quadrant, so it goes 0 to 90 degrees here. And there's 4 of those, and one for each quadrant. And I don't believe those are in the online article, but if anybody wants these individual maps, I can certainly send them to you. So just contact me and let me know. And another thing that I did as part of that article is I went through and wrote up a definition for each of those columns that are shown in the table. And I really did this for my own use because I didn't really know what a lot of that stuff meant at the time, and maybe even today I don't. But I wrote it up anyway, and I tried to use good sources. 10 years ago, Wikipedia was not nearly as good as it is now, so I have tried to avoid using it at the time. The object name, these came from catalogs, and if you go back and look at Tom Crowley's article back in the 2010, November 2010 issue of the SARA Journal, he wrote an article on what these catalogs mean. It was titled Introduction to Astronomical Catalogs. And that really helped me figure out the nomenclature that's shown in the left column of of those tables. Right ascension and declination. If you want to study up on that, certainly there's 100 million sources on the internet that'll explain this to you. Most of them right, some of them wrong. The epoch is the time reference for the observation that's listed in the table. And this changes over time because of the way the Earth drifts through its orbit. And of course, the objects in the sky are moving as well. So you'll have to, if you want to get a closer reading for the coordinates of any object, then you'll need to update the epoch that I've listed there. But for most amateur projects, I think you don't need to worry about that too much. The flux density, the spectral flux density is given in Jansky, and it's a pretty small number, 10 to the minus 26 watts per square meter per hertz. So if you can observe 1 Jansky on your system, you've got yourself a pretty doggone good system. The frequency, like I mentioned before, those observations were made at specific frequencies. And if you're going to observe at another frequency, either above or below, then you're going to have to make some adjustments. And these the flux densities on a lot of objects are proportional to the frequency to some exponent. And some decrease with increasing frequency, and some, like pulsars, for example, most of those increase with decreasing frequency until they get to a rollover point. So you need to make sure that you are using that information correctly. The other name, that's a less formal name usually. And so that's pretty much the presentation that I've got. I do have some web links and references here for you. And if you have any questions, you can contact me. But meanwhile, I want to show you one of the hazards of working in Alaska. And this is right outside my window where I'm sitting right now. That guy wandered by about 11 o'clock at night. So when I'm out mowing my grass, I carry a shotgun. So that's it. I warned Rich that I didn't have a full 45 minutes. I think I took less than 15. So please contact me if you have any questions or comments or find any errors in anything that I write. I'd sure like to hear back from you.
Great.
So thank you very much, Rich.
Oh, thank you. This is excellent. In fact, I use your picture. It's posted up at our command center. And by the way, I got a couple comments on this thing. And 1 second here, they keep scrolling down. Wolfgang came back and said, sorry, my memory did not serve me well. Cas A is actually 1672 Janskis, followed by Sig A, which is at 1550.
Okay.
Let's see, Preston, I would love the copy of your drawings. He gives a his email address, Galaxy Tab A. I'd like to recommend that you guys can, if you go to your participants list, find your name, and you go to the dots, you can change your name. Try not to put some obscure thing like Galaxy Tab A there, because we'd like to actually know who you are. But this is, he would like to have a copy too. Jay Wilson, good info, wit. And Ted Klein, what is the blue? What is the blue?
I was afraid somebody was going to ask that question. I don't remember. This was 10 years ago. I think that the blue are, the red are greater than 40, if I'm not mistaken. I think the blue might be less than 40, but I'm sorry, I just don't remember.
Now, the other thing is 400 megahertz. I've been asked that question a couple times, and I don't know the answer, why they even made a map at 408 megahertz. What's so special about that frequency?
Well, that map is actually quite old, and maybe in those days that was their technology. I'm guessing on that, but a lot of the objects in the radio sky are pretty bright, or brighter at 408 than higher frequencies. So it's possible that the technology of the day limited to that frequency.
And Ted came back that 400 megahertz is possibly your blue sources. And
yeah, I really don't know. Sorry.
Galaxy Tab A is Kim Hay. And okay. Thanks, Kim, for identifying yourself. Let's see what else. By the way, this is a great, this article is a great article to print out, and you start observing, especially to find out if you're actually looking at anything real. Because if you can't, my guess is amateurs really can't pick out anything but the big reds and the blues on this chart. And if you're not looking at that, you're probably looking at noise, and that's my experience.
And so the 408 mystery continues.
That's it. That's it. No one knows. Now I understand, and maybe Wolfgang could do on this, that the for pulsars, 408 seems to be like one of the peak signal levels on pulsars, and then if you go down to 1420, it actually decreases. So that that appears to be a number.
Yeah, many of the synchronous radiators that's referring both to pulsars and many other sources, they sort of peak around the 400 megahertz range and then they drop off. And that's in contrast to thermal sources, which increase with temperature, with the frequency. For example, if you look at the moon, it's pretty low at 400 megahertz, but when you go to a couple of gigahertz, it really gets bright. So if it's a thermal source, it increases with frequency. If it's a synchrotron source, it decreases.
Okay. And I got from Fred Erskine, 408 is a protected radio astronomy band. You got to join the subcommittee, Fred. That's probably another one, is that it's a band. That's where everybody looks, and so that's where they want us to keep looking. Okay. I think that's it. Outstanding, and what that's what I'm saying. One of my goals in life, besides getting as many pulsars as Wolfgang, is writing as many articles as you. Right. So keep plugging away.
Thanks,
on the. I really you're an expert on the journal, and you're always there.
And Rich, I'm gonna I'll copy down these email addresses to people that are interested in the maps. If I don't get them all, though, maybe what people should do, if they want the map, send an email to me. And
there you go.
My address, email address is shown in that in the presentation and also in the article. So have them contact me and I'll send it out.
Okay. I got from David Fields, those of us who use Radio Eye's planetarium program can select 408 megahertz or 21 centimeters. Background, do you use it?
What was that again?
From David Fields, those of us who use Radio Eye's planetarium program can select 408 megahertz or 21 centimeters background. And he wants to know if you use that.
Oh, yes, I use Radio Eyes. That's the premier program as far as I'm concerned for finding specific objects.
All right. And we do have one more license for Radio Eyes on the next raffle. So if you guys want to get that, and you can get a free license for that. Okay. Anybody, anything else for Whit? Okay. We're a little bit ahead. Ray, you wanna go ahead and go? I'll give you a quick intro. And actually, I'm sharing this. We're gonna do sort of a joint one here. I've got the slides for Ray here.
Yeah, I'm ready to go.
Okay, one second. All right, can everybody see that? All right.
Yes.
Ray Ubereken, AA0L. Ray's lifelong passions for astronomy and radio began in Cub Scouts. He became a licensed amateur radio operator in high school before entering the Navy in 1955 and has maintained his license ever since. Now licensed AAOL, he obtained a class as extra in 1978. He put ham radio and astronomy together as a hobby in the 1960s, doing moon bounce and measuring sun and galactic noise. He maintains radio and optical observatories at his home east of Colorado Springs, Colorado. Ray's employs a broadcast engineer babysitting 2 AM and 4 FM stations. Ray's a long time member of the Deep Space Exploration Society. Enjoys building receiving equipment and feed antennas for their 18-meter dish in southeast Colorado. Ray is also a member of the Colorado Springs Astronomical Society, Society of Amateur Radio Astronomers, American Radio Relay League, and life member of AMSAT. Current interest in is cosmology and proving the various theories of how the age of the universe is calculated. Ray's work on pulsars and result measurement and dispersion measure is an excellent input to his work. And I have to say that we have that tower that is behind me that we changed the feed on. Ray's 80 plus years old, and he's still gets up that tower faster than anybody I know. So he's still, he's in outstanding shape, and I'm jealous as heck. Ray, go ahead, and I'll flip slides when you tell me.
Okay, very good. Thank you, Rich. I've been around the DSES group for a long time now, and got back interested in it. Originally started back in around 2000 or even before that. And then I kind of slacked off for a while and got back interested in it again about 2010, 2012, right in there. And I've been associated with it ever since. But one of the things that happened, I'm going to give you a little explanation of this particular site. It actually looks like something now, but it didn't always look that way. And I've been around a long time. I actually tried to buy it back in 1984, along with several other people here in Colorado Springs. But I'll go into that a little bit. But the history dates back of this site, back to the 1950s, maybe even a little bit before. I'm not exactly sure. But the site was originally owned by the National Bureau of Standards, or the government. The National Bureau of Standards operated it. And it had a 500-foot tower on the site and several trailers and all kinds of things. And they actually measured temperature, pressure, and all that sort of stuff on this tall antenna or tower. And the actual antenna, the one that you see on the right of your screen, the dish, came along later. It actually came along in the middle 1950s. The site was actually there ahead of time. And then the site was stopped being used in about 1972 or so, somewhere in there. I know some of the guys that worked in this site, and they hated it. It sits out in the middle of absolutely nowhere. And they had to put in a couple of weeks there, and there were bunkers, and there is a large bunker, maybe 30 by 50 foot bunker that sits about 600 feet away from where the current dish is, but it sat right next to where the tower was originally. And they would go and operate from that bunker and live down there with the snakes and everything else that happened to be around. But that's all that's around. I mean, you couldn't raise one cow on this land. It's just nothing grows there practically. It's like the surface of the moon. So back in the early 50s, it was a pretty going place. And then they quit using it in 72. And later on, in about, then they have to wait about 10 years before they actually sell it once they quit using something. And so in 1984, it went up for sale. And I and several others, 5 others in Colorado Springs tried to buy it. And we knew that we didn't have any money, and so we really lowballed it and thought, well, if nobody wants it, and we couldn't figure out anybody in their right mind would want this place, that maybe we might come up and get it. We had ideas of operating it remotely from Colorado Springs via amateur radio. So we were not successful. Somebody did want it, and they bought it, a fellow by the name of Plishner. As you know, that we have called this site the Plishner, Paul Plishner Radio Telescope or Astronomy Site. So they got it, and they tried to sell it. They tried to lease it. They tried to rent it. They tried to everything they could think of for around 20 years, and never were successful at doing anything. Nobody was interested. It's not even it would cost you more to scrap it than it's worth, I think. So they had this site, and it's actually 17 acres of site, and it sits out in the middle of what would normally be anywhere else farmland, and they do farm it. But I'll be honest with you, this year, and Rich can verify this, there is nothing growing there, and they didn't get any water this year until about less than a month ago, I think. Just a matter of a few weeks ago, they finally got some water on the land. But it sits down in southeastern Colorado, near a town of Haswell. And Haswell is a town that used to be on the railroad. They have a grain elevator there. It used to have stores and things, but nowadays maybe only 1 out of 5 of the houses even has anybody in it, and it's just a broken down old, almost a ghost town. So and there's a few people living up there, but not very many. And so it's I don't know what else to say about it. It's barren. I mean, even snakes don't like it down there, I don't think, although we have found several different varieties, including rattlesnakes. So anyway, none of the equipment that's on the property now was there back in 1984 when we tried to buy this property. And the pedestal was there with the dish, and the feed tower was not there. The trailer wasn't there. None of the little buildings that we stole from the railroad are there. There was nothing except an underground bunker, which is about 30 by 50 feet, roughly, and the pedestal and the antenna. Everything else had been pilfered from the site. There was no coaxes. There was no nothing. All the radio tower had been sold off, and everything else was gone. So, and it wasn't even a gate or anything like that getting into the property. The fence had been torn down. And so the farmers do farm that land around there occasionally, but not this year. There's no crops this year. So anyway, fast forward then to about the year 2008. And, let me step back a little bit. Back in 2001, something happened in the United States called the 9/11 episode. And then along came Homeland Security. Well, DSES took care of 2 dishes like this, exactly like it, sister dishes, up in a mesa north of Boulder, Colorado. There are 2 of them up there, and that was right close to where everybody lived. And so they had taken care of these dishes after they after National Bureau of Standards quit using them, and put new motors in them for the drive system. They put all kinds of readouts and things like that. And they actually used the dishes a little bit for some science experiments at 1420 and other frequencies. So that group, the Deep Space Exploration group from up there in Denver, Boulder, Golden, Fort Collins, up in that area, northern Colorado, took care of those dishes for about 20 years. Then along came 9/11 and Homeland Security, and all of a sudden people started getting a little bit nervous about people coming onto government property. We even had our own gate, basically, that we came in the back side of it, and they shut us down. So all of a sudden, Deep Space Exploration Society did not have anywhere to operate. And so this dish became available. Some of the guys were energetic enough to contact Mr. Plishner, talk to him a little bit, and he donated the dish to Deep Space Exploration Society. So after all those years, I actually got it for nothing. So, and you can have it too for nothing. $50 a year dues. So anyway, the people in Boulder then started, because they had to get off that site up there with the other 2 dishes, they started moving all of the equipment that they had been able to energize those dishes with down to the Plishner site, or down to Haswell. However, Boulder's a long ways away, and it was a long drive for them. So they would come down to this site and live in that bunker. And then when they finally got a trailer moved down here, they actually, one of the guys had a bunk in there, our little sleeping bag. that he slept in. And so they came down about a week at a time, a few days at a time, and they would come down and work. And they did most of the work, early work. And so Rich and I and Bob were standing on the shoulders of these guys that came before us and did much of this work, getting the drives ready and actually moving the antenna. The antenna sat in a bird bath position for about 40 years before it actually moved in 2012. So the guys came down here and worked at it and got it going between 2008 and 2012. Now understand that there is nothing, there's no stores close to us. There are no stores in Haswell. About 30 miles away, you can get to some stores like a Walmart or a Home Depot or something like that. But you got to drive quite a way, and you have to drive that far for restaurants. You have to drive that far if you're going to stay in a motel. There are no stores really in nothing that you recognize as a store up in Haswell. So it's a long drive and it's difficult. Well, the people in Boulder had to drive a couple 100 miles to get here. And so it was a long way, and they would come down for like I say, several days at a time. Well, they got tired of that after a while. And about that time, some of us from Colorado Springs got very interested in it. And we started coming down here. And so slowly but surely, we got a bunch of people. And I know that Wolfgang yesterday mentioned something about there's usually 10 or 20 people that do most of the work, and everybody else is members only. Well, that's the same down here, of course. And so we've always had only about maybe 10 people doing most of the work at any given time. But those 10 people stand on the shoulders of the ones that came before them. And so do we. And so a lot of people did a lot of work at this site, and still continue to this day. Some of them do software, and some of them do hardware. It's just a little bit of everything. Anyway, about 2012, it moved, and I was there the day it actually moved for the first time in 40 years. And so it was very exciting, and I just got all back into it from at that time and started coming back down. And so nowadays I work on feed antennas and some electronics. I build various things. So that's why we are very excited. And this has been a long, drawn out 12 years getting this site to where it gets its first Pulsar. And we are excited to be the ones that actually did that. And everything here that you see at that site, the drive motors have been replaced. They're all different. Initially, this place had 480 volts or something like that coming into it at like 900 amps. It was a huge amount of power coming into the site. But in the meantime, once the National Bureau of Standards quit using it, the power lines fell down. The place didn't have nobody was using any power, so they tore out all the power lines. So we've been working all this time, first of all with a 4,500 watt little portable generator. Then I got him a 25 kilowatt generator, and one of our members got that working for us and got it all up and running and wired the place. We buried cables from all of the buildings, from the tower to the trailer, and over to the bunker. And now we have, thanks to Skip Grilly, we have power at this site. And we actually have AC power. You can go in there and turn on a switch and something happens. And you don't have to go out there and kick the generator 14 times or so to get it to work. So anyway, nowadays, it's much improved over what it was. There's all kinds of activities and things going on around there. We have various antennas for different things. We have a complete ham station. The bunker's all been restored, although it blows in with sagebrush so much that, or tumbleweeds, that we don't actually go down it for help anymore. I don't think Rich and I have been down there in a long time. I'm just reading here a couple of comments. Yes, AT&T and T-Mobile work off of Yellow Towers about 15 miles away. And yeah, we don't have internet at the site at this particular time, although we did for a little while. And so anyway, it's now getting into good shape where we can actually use it. And we, in driving down from Colorado Springs, I should talk about that because there's no place to really comfortably stay down here. Some of our guys do stay down in overnight and down in the bunker, but it's not a fun thing to do. And so we mostly drive it and come down here one day and go back home. That's about 5 hours driving time for the average person. It can vary anywhere from about 4 to 6 hours, but its average driving time is around 5 hours for us. And so out of your day, if you spend 8 hours down here, that's 13 hours. You've spent a long day and it's been a hard day. So to come down here and particularly at night where you're going back in the middle of the morning, it's pretty tough, particularly for us old guys. And so nowadays we're going to have internet here in a couple of weeks, and that's going to improve things considerably. So let's go on and talk a little bit more about the actual dish. As Rich changed it here and in our Pulsar work. So Rich shows you the feed on the right-hand side. I built that feed, and I built what we call the quick change harness below it. This top of this scaffolding that we go up to work on the feed antenna, the feed antenna goes right over the top of scaffolding. And so, but it was very difficult to get around the front side of it and actually put new feed antennas on. It was downright dangerous. So we do have tie-offs on the feed itself when we go up there with our safety belts now. But so I built the feed mechanism, the quick change mechanism that you can see, and then the feed antennas that I build will all fit into that, and they'll all just slide in, and 4 little 1/4-inch bolts, tighten them down, and you're all set to go. And then there's a feed box up there that can house preamps and relays and all that. And when we do the moon bounce, we'll stick the moon bounce equipment up inside the cavity up there that you see behind the feed antenna. There's enough room in there to put some even rack-mounted stuff, if just 1 or 2. So anyway, the feed antenna, and the reason I chose it was because of we had a lot of data at 408 for pulsars, and we wanted to go after pulsars. So I just arbitrarily said, "Gee, let's go there." Pulsars seem to be really strong there, and that for us getting just this operation of this site going for the first time, very important. So we wanted as much advantage as we could get. So the dipole feed is an EIA dipole feed, EIA standard gain antenna. I saw it used up at the Boulder sites back in the 60s. So I thought, gee, why not use that? And we'll start out there. And so that's what we did. That's what you see. However, if you'll think about this dish is not painted white. And there's a problem with that. If it's painted white, it disperses energy, light, and also hopefully infrared, the heat stuff. But this dish is just plain aluminum. And so if you aim it at the sun, guess what happens? You melt the feed. And guess what happened to this feed? I just took it down on this week, Saturday, and brought it home, or Friday rather, excuse me, brought it home, and sure enough, the sun, when we were tracking, I think it was the crab pulsar, it was too close to the sun, and we melted one of the little plastic pieces that holds the dipoles. And so got to replace that. But it didn't hurt the antenna. The antenna still operated normally. And we have a new box up there now that shows all these coaxes terminated a little bit better. So it looks much nicer. But I have a 1420 megahertz feed that also slides in to that quick change harness. And it has a latch, and so it folds down underneath what you see there. And it's right there where we can sit on that platform and actually work and change the feed antenna. So it's much safer, no hanging over things like we had to before. And it's much lighter as well. So let me go on here and talk about the rest of it. We have a very simple preamp up there at the antenna. It's about a 0.5 dB noise figure. maybe around 40 degrees Kelvin. And it's runs about 30 dB, a little better than 30 dB worth of gain. And then that goes immediately from, it's right at the back of the feed antenna where there's a balun. It's located right there. And then from there, pipes it into another preamp inside this preamp box that we have up there. And from there, goes down through a 1/2-inch Helix coax of about 200, 210 feet long into the trailer. We have 2 coaxes running up there, but they are not the same length. They go different routes. We put the other ones in a little bit later, and then this one. And so then there's the other preamp runs just about the same noise figure, and it runs about a little less gain. So we have a roughly about 50 dB gain overall up there at the dish before it comes down through the coax. So the noise figures is well determined right up at the feed point. And see that? Then we feed everything with 12 volts through the coax with the bias T. And Rich will tell you all about bias T's. He knows all about those. He burned up. He's burned up at 1 or 2 himself. So anyway, that's I guess that takes pretty much care of everything up at the tower, up at the feed antenna. Down in the trailer, we have the EDIS N210, and that is the SDR that was donated to us from one of our members, and he said he was not using it. In fact, we've had a second one donated that same way, and Rich can cover that a little bit here. But this is the hardware that we used for detecting the pulsars. That goes into a standard laptop computer, and then Rich loads up all the software, and away we go. Now, one of the other things that it's gone on. Wolfgang asked what is the F over D? The F over D ratio is 0.41 actually, and I have a 3.7 meter dish at my house that has a 0.4 F over D. So everything that I build to take down there, except the 408 antenna, I test at my own house. I've got a 1420 and a 1296 all set to go down to the dish, and they're done at my house. So now we go to this the EDIS, and that's really the power of the whole system. Although we've had a lot of trials and tribulations trying to learn how to actually operate it correctly. And then the software, the GNU software that we use, Rich has up there right now, shows you where we adjust the gains and set the bandwidth, and we're trying to do everything. But we're limited to about 20 megahertz or 25 megahertz with this, and most of these pulsars were all done at 10 megahertz bandwidth. We at first did not receive the signals at all, and we were really disappointed on our first trial down there. And then we said, maybe we should back these gains all the way down. Maybe we're not operating even linearly. And so we did, and sure enough, the pulsars were there and came right out. And that pulsar, the 54 pulsar, we call it anyway, the declination of 54 plus 54, we can see that one because that's circumpolar. We can see that all the time, and we always go to that one first up there to make sure everything is working correctly. So let me go back here. Yeah, Rich is showing you some RFI. That's not necessarily all RFI, but unfortunately, they said the reason you choose 408 is because 406 to 410 is a protected band for RFI for radio astronomy. Well, not down there, it isn't. We have a cell tower, and sure enough, they got all kinds of crap coming off that cell tower right in the radio astronomy protected area. So we have to mitigate things. That's why we actually moved our 25 megahertz or 10 megahertz bandwidth up a little bit to about 420 and center frequency, and that's where we actually detected the pulsars at. Otherwise, we have to contend with all of the interference from that cell tower.
Got one question about why we don't put the SDR directly at the feed point.
There's no need to. It would be more difficult. the SDR, the noise figure of the system has already been determined. So it is more than ample signal for the SDR, and there would be no benefit to putting it up there. In fact, it would make it a lot harder on us because we're continuously moving things around and testing it, and that would make an awful long USB cable. We'd have to stretch that because it runs off of USB power, and so yes, we have to keep it down by close to the computer. Now, I should also tell you that we didn't for a long time have any heat or any air conditioning down there, and this is Colorado. It gets cold and it gets very hot. But nowadays we have 2 air conditioners running in there. We have full-time power, and we have everything up. Boy, I'm over time here, I guess. Maybe not quite. Okay. Okay. So we have this is one of the 2 or several of the guys developed the software. Everything is hand done. It's all done by us. It's not, we didn't purchase anything. These guys actually, other than the EDIS, and that was given to us, but these guys actually wrote all the software, and they have this is the computer that maintains us on target. And so we've been doing it manually by moving, if you can think of these little circles, concentric circles, those are like the a bore sight or a scope sight on a rifle. And so we move that in relation to the target. So the target, if we move the circles down, they stay where they're actually put on the screen, but the target comes up into the center of it. And we try to keep it there. The center part, the yellow trace, is actually about 0.15 degrees radius. So it's about 0.3 degrees across. The other one's about 0.5 or so, 0.6. And then, so we can keep it easily within the 3 dB beam width of 3 degrees for this antenna, for this bead. And so it's done by a couple of manual switches, and we kept moving it. Boy, I've got some good news to tell everybody. A week ago, these guys that wrote all this software actually got it to run the dish automatically now. We have, instead of manual control, we now have automatic control, and it's a pleasure. We actually ran out of things to talk about. We didn't have to pay attention to those switches all the time, keeping it all centered while we were trying to make the runs. And the runs can be several hours long, as everybody knows. And so it was kind of we'd lose attention every once in a while to the project at hand. And so we eventually now have automatic control, and it's no problem for us anymore. Go on to the next slide, Rich, unless you want to say something about it.
Oh, good. Go ahead.
Okay. There's the other member of the group. That's Bob Haggart, and he's out there. He built a very nice bench while we were doing some of this, getting it all ready to go. And he was building a bench inside of the trailer. And so when Rich got done with his first Pulsar run, he took it over and set it on that brand spanking new bench and found the first Pulsar. So that's number 54. That all of a sudden, when Rich got the timing right on it, it just popped out, and it was there for sure. We had finally done it. Go ahead, the next slide. There's Rich and myself, and we're pointing toward our success. And I'll tell you, we were a lot happier than what what shows there. We were really, really excited, and as culmination of so many years and so many people doing work at this site to actually get it to this point. And you see behind my head is the manual control. It's got a couple of regular old toggle switches on it and a couple of knobs, and those are the speed knobs for azimuth elevation. And there it is. And we have a couple of switches to raise and lower and left and right, or clockwise and counterclockwise. I might point out that underneath the spectrum analyzer is where I've recently done all the coaxes, cleaned them up, and got them all wired in. And we have preamp power just below that. We have a spectrum analyzer that we do always check And in between runs, we often check just to make sure that everything is still working. Over on the left, on the lower part, I might make a comment that is a signal generator, and there are a couple of computers below it and a screen behind it. And that stuff belongs to Skip Crilly and his experiment with the SETI project. So we have actually been working with Skip also. So anyway, that's mainly our control. Not anything like the Stockard-Pelier, Astropelier group, but or Astropelier Stockard group, but it's certainly it's a lot of equipment for us. We didn't have anything before this. So back to our pulsars. You see the pulsars and the lines going up through, and the dispersion measurements and all of that. But when all was said and done, and Rich got the timing trimmed, everything fell into place, and it was a great day for us. Let's see, we have that in here, I think, don't we?
Yeah, we do. And I want to comment on this thing. This is what it looked like. I used Tempo, which is the timing software. This is the raw data, the first that came out. When we saw those lines came up, we just knew we had it, even though it wasn't tuned up yet. That's the first pulsar ever before any tuning happens. But you tell it's there, and you just haven't tuned it up yet. But that's the most exciting time we've had, is that picture there.
Yes, and the next slide shows you a better, that's after Rich cleaned it up some, and you'll see where the dispersion measurement came out right where it's supposed to, and everything really looks clean. And we go back to this same pulsar all the time because we stow the dish at 317 degrees and declination, or straight up at 90 degrees, straight up in the bird bath position. But the first thing we do is we tilt it down to the horizon, and over in that northern part to the north is where we always can find this 54 pulsar, so that we go over there and look at it and check out and make sure the system is working. It only takes just a few minutes. And then Rich also did some pulse width measurements on it, and this is the very bottom of the page. And
yeah, the Presto software produces a text file that allows you to pull that into Excel and it does one pulse period of data from your analysis. So you pull that out and you plot it, and this is what it looks like to plot. But one of the key things there is that you can actually zoom in and try to analyze the pulse width. And this is and the main number there is that the 50% of the height of the pulse is called W50. That's in the ATNF database, and that, you know, this thing at plus 54 is 6.6 milliseconds, and just from the numbers here, I was able to get 6 milliseconds measurement, which helps you confirm that you actually got the pulse, or you actually got the right pulsar. So we do this on all the pulsars that we get, just to verify that it works. And it was interesting. The one we just got was the 1133 plus 16, and the pulsar was 3 times as wide as it was supposed to be. And I confirmed with some people that was actually considered a large pulse. I mean, it's a unique thing that happens with that pulsar. So we're going to get some science out of these things, and we'll write that one up for one of the journals here. But that's a very important thing, is to grab that raw data and plot it. Go ahead, Ray.
Yeah, well, I'll go ahead and talk about a couple other things that we're going to do with it in the last few minutes here. Last minute. The next thing is Skip and Steve Plock are going to be doing some SETI work, and they're also going to, with one of our other fellows, Tony, going to set the system up and with 1420 feed on the dish, And I took the 408s already down. The 1420 is going up very soon, and they will actually double check the actual alignment of our readouts to make sure and make any corrections that we need to make for the higher frequencies as the beam width goes down. And then right after that, in October and November, we're going to do some moon bounce on 1296 with the dish. So, and some tropospheric scatter work with maybe down as far as Texas and around. So we're going to put my 1296 system on it, and we will be on the moon during the ARRL moon bounce contest weekends for up to 1296, and that will be on October 10th and 11th, I believe, and then the latter part of November, around Thanksgiving time. And then after that was over, then we will put my 1420 feed on there and see how it compares to Steve's, and whether I got my system working well enough to do some. And then we'll start working on pulsars on 1420 for a while until the earlier part of the year. So we probably for the next 6 months at least have the system tied up with different studies. I think that ends it, Rich.
Yeah, and I want to tout Ray's ability. Ray made a Pulsar simulator that produces pulses at different Pulsar pulse rates and different pulse widths. And I've been using that. I actually have that tied into the receiver and to the computer here, and I'm able to generate pulsars that Presto picks up as pulsars. And I can change the, we got a frequency counter in there, and I can actually produce pulsars with this little box. And he's actually gonna, right now he's got it sort of crystal controlled, but he's gonna put GPS timing in there, and we're gonna have very precise stuff. So that has been such a learning opportunity we test all the different modes on the Presto software and the GNU software and et cetera. With this this tool, and we'll put something together on that, because I think it has tremendously helped us learn the system, and is a great training tool. Okay. Okay, that's all we got. Any more questions? Okay, we're running a little ahead, so Bruce, cue yourself up, and we'll go ahead and
Hey,
so
Rich.
Bruce, yes.
Yeah, my video is apparently blocked by you, because I tried to hit the start video button, and it says that you've blocked it. Can you check on that?
Yeah, I was sharing. Try it again. You can't do it while I'm sharing, but go ahead.
No, it comes up and says you cannot start your video because host.
Okay.
Remember, I got hung up when you unhung me when I was doing the secretary thing.
Absolutely. Let me. Okay, let me try to get you here.
Okay, it popped in.
All right, great.
Okay, yeah, see me. All right, that's good. So get started. Let me get all my notes in order here. And
okay, well, let me give you a. Okay, and we're a little ahead of time, but that's okay. Let's see, Bruce Randall. He was born a long time ago, so he's getting to be an old timer. I'm not going to say the date. Bruce got his first ham radio license in 1966. He presently has an extra class license with a call sign of NT4RT. The RT is the call is for radio telescope. Bruce has worked as an electronic engineer since 1978, with involvement in analog circuit design, power supplies, a bit of DSP work, and some antenna design. His hobbies include astronomy, ham radio, and radio astronomy. Bruce also enjoys canoeing and hiking as time permits. Bruce has been a SARA member for over 25 years. He's now a life member. His experiments with radio astronomy started in 1990 in the days of the chart recorder as the output device. He's interested in interferometers and possible extended baselines in the future. Bruce has been on SARA board in the past and is presently SARA secretary. And great. Bruce, yeah, you can share your screen if you want.
Okay, see if I can make that work here. Share screen.
All right, it's coming up. Good. I can see it.
Start your video because the host has stopped it. What?
No.
From beginning.
Nope, it looks like I've still got you on video.
Okay, there it opened up. Okay,
Right.
seem to have it. Okay, so talking about capacitors, and actually I was wanting to, I'm going to unshare for a minute here if I can find the button, because I wanted to just show around the room a little bit. Well, I'll do that afterwards. Anyway, capacitors store electric charge. If I can find the, I got my laser pointer on. Yeah, you might think of this as a unit of charge. You know, after you've been working out in the yard with a lawnmower, that unit of charge can sometimes help you a bit. But it actually has some resemblance to the Leyden jar, which was the original capacitor. Originally, they actually put liquid inside it because they thought the charge was held in the liquid. Ben Franklin was actually the one that discovered the charge was held in the glass itself rather than the liquid. But you can see the bar up there. So actually, I could have taken that, pulled the cap off, and put a rod down there with a ball on top of it and used the thing of Corona as a Leyden jar for whatever that's worth. Okay, a capacitor, we've got a dielectric or an insulator, the glass in the Leyden jar, a metal plate and a metal plate, and some kind of connections to it, and variations of this construction here. It's basically, well, we got a schematic symbol that we commonly see for it. Yeah, regular capacitor and electrolytic and variable capacitors. You got to remember it's a storage unit for electric charge, and that charge is basically an accumulation of current in the capacitor. Got the seahorse there because integral sign is sometimes seen as a kind of an intimidating thing to people, but seahorse looks a little friendlier there, so I've decided integral signs are really a seahorse. I guess 2 seahorses would be a 2 pair making a family, and 3 seahorses. Well, let's not talk about that, but everybody's had to solve a triple integral would know about that. But anyway, voltage on a capacitor is integral, which is basically just summing up the result of current over time going into the capacitor. You can see down here, I've got my bucket of water and a faucet flowing into it, which is essentially the same thing there. You can see the, oops, did I get that? There we go. So we can see the water flowing in and the water accumulates in the bucket. Basically the same thing. Instead of, electrons, it's water. We're filling up a bucket, a container, a capacitor, and on there. Now, lots of times for work, like I've done a lot of work in switching power supplies, and it's more common to use this form, which is basically a little scribbling from calculus class, and you can get from this form to this form of the capacitor, and generally more useful. And then there's another form that we use that commonly, which is the X of C, which we're looking at as an impedance. So you can more or less use sort of an Ohm's law type of rules with capacitors. And that's derived from that above. And there's a whole lot of calculus to get from this to this. And it's, it's a pretty nasty calculation. But this is much easier to use for somebody who's working anything frequency domain, like solving RF filters on a switching power supply is a common use of it. And by the way, there's actually a J in front of this here to tell you that it's a 90-degree phase shift of the impedance. And it's not just like a resistor, but for a first shot look at things, lots of times that's all you need. And that's what they normally put in like radio amateur's handbook or technician's literature. Another way to look at the capacitor is you put the capacitor with the resistor, and you have the capacitor will charge to the resistor and from a voltage source. And as the capacitor charges up, the current through the resistor drops so that it turns into an exponential function there. And that's lots of times used for timers that 0.694 times the value of the resistor times the value of capacitor will tell you how long it takes to get to 50% charge, which is used in a lot of circuits. Or if one RC time constant, it'll get to 63 point something percent there. 63 is a good number for a first shot at it. So that's lots of times used in timing circuits, timing circuits, filter circuits, and things like switching power supplies and integrators and things. You get to that. What's our capacitor good for? In some cases, it's kind of a measuring cup for charge. I mean, there I'm, getting ready to make pancakes one Saturday morning there, and pouring the, soy milk, which we have to use because we're allergic to cow's milk. But anyway, pouring that into a thing, and we're going to carefully measure it. And so, measuring cup with charge, again, we'd have places where it'd be used in integrator, timing circuits, filters, resonant circuits, A to D converters. Those things, you're making an accurate measurement. So you need a capacitor that's quite accurate. Other cases are more energy storage, like power supply filters and bypass capacitors, coupling capacitors. Those are much less critical. It's kind of like the mixing bowl. The exact size doesn't matter as long as it's big enough to hold all your ingredients when you pour them in there. You're good to go with that. So here we're going to compare our measuring cup to a capacitor. In this case, I've got actually a kind of antique polycarbonate capacitor, which is a very high quality part for accuracy. But anyway, measuring cup, we want it to be a pretty exact size. A capacitor, we want a pretty exact value. You need a rigid shape for the glass here, so when you pour liquid in it, it doesn't stretch. Capacitor, you want one that it doesn't change with voltage. You really wouldn't see temperature effects on a measuring cup normally, but still, it's something made out of Pyrex glass. It's going to be stable with size. Same with the capacitor. A good capacitor is stable. If you had a measuring cup with porous sides, you'd get some of the liquid go into it, and you wouldn't get it out right away. And that would be like dielectric absorption in a capacitor. I'll talk a little more about that later. And no leaks. If you had even a pinhole leak in here, throw off your measurement. Same with the capacitor. You want something no charge leaks out. In other words, it should be pretty well perfect insulator. Now here we're going to look at just a storage container or mixing bowl capacitor. I've got here a picture of a electrolytic capacitor, which are normally used in power supplies for energy storage. And the value is pretty sloppy on those. I mean, some of the cheaper ones are marked -20 plus 80% on tolerance. In other words, they can be 80% higher than marked and still shipped as a good part. And again, like the mixing bowl, the size isn't critical if it's a little bit big. If it's too small, you definitely have a problem when your mixing bowl will overflow. And if your capacitor is too small, you have problems with a unstable power supply. The sides, you could mix in a soft plastic bowl with stretchy sides, wouldn't really hurt anything. Again, the electrolytic capacitor, change the capacitance with voltage. Well, we're just storing amount of charge. It doesn't matter. Little leakage would be okay. Actually, on the mixing bowl, you probably wouldn't tolerate any leakage because make a mess of your kitchen. Take a look at another thing in a water system for a house. I like to have analogies with something you can put your hands on. Electrons, you can't see them. You can only see their effect with instruments, whereas water, you can see it, feel it. So my house on a well pump, so you got a tank there, and the pump cycles on and off. It'll bring the pressure up to 50 pounds in the tank there, and then it'll go down to 30. But the pump itself, the pressure coming out of it is either 0 or full steam, and the tank is leveling it out, just like a big capacitor in a power supply will level that out. There's another thing. Okay, so that's for slower changes. Now, sometimes you've seen the thing where you suddenly turn off a faucet, or, washing machine valve changes and the pipes rattle, that kind of thing. And they put these hammer arresters on there, which are basically something, they have an air cushion in there, and it allows it to store up a little bit, and it reduce the impact of that. And on digital logic chips, you have the same problem really, that you have you know, chips pull currents in big crazy spikes, and you need capacitors very close to the chip to handle it, just like these things need to be close to the washing machine to stop the shaking pipes. So there'll be little bitty ceramic capacitors, either that or little chip capacitors, but they're right close. Take a look at ceramic capacitors here. There's two different flavors of ceramics that seem to float around, or basic flavors. There's a class 1 ceramics, which are very stable. They're using filters, timing circuits, somewhere you want to actually have a precise capacitance value. They have a whole bunch of flavors. The C0G is the only one that you normally see in engineering, unless it's something very specialized. Then you might see some other stuff. Ceramic capacitors will look like this, and you can't tell a class 1 from a class 2 from looking at it, other than the case size gives you a clue that these are quite large and bulky for a given amount of capacitance. Class 2 are very small. However, they're not very stable in capacitance value, and they're microphonic. And they're also speakers that if you hook one to a signal generator and drive big spikes into it, you can actually hear it singing. Or if you bang one while it's hooked to a scope, you can actually see it puts out voltage pulses from mechanical force. So got a lot of bad behavior, but it works perfectly well for the thing of power supply filtering on logic chips. I mean, all the hundreds of logic chips we have in everything, those capacitors right near the chip are very critical, and they're almost all class 2 ceramics. They got to need to be small, cheap, and and do the job, which they do. There they've got several ratings, X5R and X7R. If you're going to a catalog buying a capacitor like DigiKey or Mauser, one of those suppliers, those will be basically stable over temperature, won't wander around much. There's Z5U, which they'll try to sell you. It's cheaper. It's only usable for indoor applications. Then you see Wi-Fi-V, which I never put either of these two in designs. I always put these because they cost only slightly more, and most of the equipment I had designed over the years had to go in outdoor environments. They look at the temperature coefficient of those capacitors. So what happens when you move the temperature around? Now imagine we're putting this capacitor on some logic chips or some things that out at the dish feed, some electronics out there. There's lots of times you turn up with electronics at the dish feed, it gets exposed to temperature extremes. If you put X7R or X5R capacitors, the same curve, only doesn't go quite as far on the high temperature end, you can see everything would behave fine over minus 55 to 85 degrees C, or X7R all the way to 125 degrees C. So any temperature you're likely to expose it to, the capacitor just sits there and does what it does. Not a super capacitor, but it's very stable, relatively stable over temperature. The Z5U, you can see if you put it in an indoor application where you might see 50 degrees C, maybe 20 to 50, it's reasonably close and likely to work. Wi-Fi-V, put that capacitor in there, your equipment heats up, the capacitance drops, and you don't have enough capacitance on your logic chips, and they start doing crazy things, or op amps, they start oscillating. All those things need a minimum capacitance to behave. So if you're buying capacitors at any project, even if somebody specifies one of these others, just get an X7R. You'll be happy that you did it if you expose it to any temperature. Okay, and then what's the dielectric material? Oops, I grabbed the wrong thing there. There we go. So we have the polyester film capacitors. They're made out of a plastic, just like polyester, and for clothing and stuff like that. Same thing, polypropylene. You see those in a lot of normal day-to-day applications. Polyester, it has a good electrical characteristic, small size, and cheap, generally good. If you have a need for a really precision capacitor in larger values than you want to go with ceramic, polypropylene is good. It's a little bigger than the polyester, but its electricals are super good. And these look the same as those. It used to be years ago that the makers of polypropylene in these little boxes always used green plastic, but About a little after 2000, they stopped doing that, started using all different color plastics. I kind of like the color coding of green was polypropylene, but they did away with that. These do cost more. And then, of course, most modern electronics is surface mount assembled by robots. And there we have the PEN capacitor. It's PEN because nobody other than a chemist can pronounce the name of it. So that abbreviation is used. And that's similar to a polyester, except it's a surface mountable part. It's made out of a plastic that you can expose to extreme soldering heats, and it doesn't fall apart and change value. And then they've got the PPS, which is similar to polypropylene, but it again will withstand all the abuse of the soldering process. And it's a super good capacitor for applications like timing or filters, whatever. Then we have the electrolytic capacitors. They get a very large amount of capacitance in a small space, so they've got a value associated with them there. So you get a small size. It's interesting, the electrolytic, aluminum oxide is actually the dielectric, and they're made by, you take 2 pieces of aluminum foil and you put paper soaked in a magic chemical goo, which is secret formulas, but anyway, in between those two, bring wires off the 2 foils, you wrap it up in a jelly roll and put it in a can, and you don't seal the can because this electrolyte material is super conductive. So it's got a conductive path between the 2 aluminum plates, or it's shorted when it's first manufactured. And then they run a current through it, which causes aluminum oxide to form on one of the plates. And they keep doing it at higher and higher voltages until you get to somewhat, if it's a 50-volt capacitor, they may do the final forming at like 75 volts or so. And then after that, they get, a capacitor will always work reliably at 50 volts. The aluminum oxide is that thick. So it's small size, large capacitance. The electrical characteristics are pretty poor, but hey, good enough for an energy reservoir and a power supply, which is what they're used for. Then you have a tantalum dielectric, or tantalum capacitor. Tantalum oxide is a dielectric. They're made by kind of like the electrolytics, but the electrolyte material is solid. They're more stable and they have very little leakage current. So they're sometimes used in timing circuits where you need a bigger capacitor and you get a couple hundred microfarads of those. And then we got various variable capacitors show along, which we'll go over. You got the air variables where the air between these plates as they're moved is the dielectric. And then you got ceramic. There's a little ceramic disc rotates over a metal plate underneath, and you got them made out of plastic film. Then there's the piston air capacitors, which are interesting. These first 3, they're usable to maybe 400, 300 or 400 megahertz. They still behave reasonably well. These are very low loss and will work to a couple of gigahertz. So they're lots of times used in the past in preamps. More modern preamps are lower impedances and don't need those so much. Then there's another capacitor floating around, the porcelain capacitor. It looks like a ceramic in construction. However, porcelain is very, very low on losses. And a little capacitor, 1/10 of an inch long, can have kilowatts of power going through it and not explode or melt down. And because of the low loss, they're lots of times used in preamps now, where we used to use the piston trimmers. They put, fixed capacitors because the FETs for preamps have much better control now. But the porcelain, I said they're almost lossless. And any other capacitor you'd add to the noise figure of your preamp, not a good thing. Take a look at an equivalent circuit of a capacitor. You got your basic capacitor, what's marked on the case. Then you got a resistor inside in parallel with it, and all these other components are undesired things. You have some series resistance there, and then because of the structure of it mostly, you have some inductance there, and these things can be headaches sometimes. And then we have dielectric absorption, was an interesting thing. To have a capacitor, let's say 10% dielectric absorption, this capacitor, which is kind of a phantom, would be 10% of the value of that one. But it's got a very high resistance in between. So if you charge a capacitor up to a high voltage, the problem in like radar power supplies, you can have 5,000 volts sitting on an oil-filled capacitor. You think it's discharged, you let it sit a while, and this capacitor held some charge, discharges in this one, and all of a sudden that capacitor was sitting there, you thought was discharge has 500 volts in it. So it's mainly in high voltage places or precision measurements are the two things where dielectric absorption gets you, because you don't want the capacitor to misbehave in any way. I go to series inductance because that's the thing probably the most interesting to us. And this would be like for a typical chip capacitor, you have 0.8 of a nanohenry, very small amount of capacitance. But that will form a resonant circuit with the capacitor and cause it to, above a certain frequency, the capacitor ceases to look like a capacitor and becomes an inductor. This is from some of Howard Johnson's work. You notice this one's 20 years old and still applicable. You just move the things around a little bit. But a capacitor will have a range where it bypasses noise on a logic chip, and beyond that it won't. But the inductance is lots of times a headache in a capacitor. Here we are, a little disconnect with reality here that happens. You mount a capacitor to a circuit board, and the capacitor when it's mounting would have this area here, because inductance is associated with a area enclosing a magnetic field. So we got this area here enclosing the magnetic field, except when we mount it to the board, the whole path to the IC we're bypassing goes like this and this. So all of this area adds to the inductance, and we don't have adequate bypassing at the capacitor at the IC because of too much inductance there. So that's critical in logic chips, among other things. This capacitor would in fact be mounted in a different manner so that it's much closer to the IC chip, because the chips can misbehave. Memory chips forget things, and flip-flops flip the wrong way, and other bizarre stuff due to the capacitors not being good enough. So the proper mounting of the capacitor next to IC chips is possible. That also gets into the area of radio frequency interference. Every digital logic chip is a radio noise generator, sometimes a pretty strong one. As a matter of fact, DRAM chips are among the worst because they're clocked at a constant speed, and it can run you kind of crazy. But the mounting of the capacitors is very critical in something like that. And it's mainly because of the undesired inductance that you accidentally made in your mounting method. Now we're going to go to the feed-through capacitor, which is of some special interest there to us, as we'll see in a minute. Feed-through, you've got you can see the construction of it. There's a bar there, and the capacitance is between that bar going through it and the outer housing. This one's mounted with a threaded nut. This one would be soldered into a wall. This is a surface mount one, which works nowhere near as good because it's not going through a wall. But because of its construction, the stray inductance sitting here can be very, very small, and it results in the capacitor being free of resonant effects on this part of it, all the way out to 10, 15 gigahertz lots of times with a well-constructed capacitor. This may sound kind of academic until the next slide here, but anyway, we've also got the inductance related to these bars here, which is somewhat larger, but that's in series. This is the point we're trying to keep signal from getting from here to here, so series inductance doesn't hurt us really, but we need the very good path here. Then the feed-through capacitor is mounted in the wall of the box, and soldered or bolted in. So that box leaves a protected area. And if the feed-through is properly installed, radio signals, noise, whatever out here is effectively bypassed to ground by the capacitor going through the wall of the box. So you have a protected area here. The feed-through capacitor becomes part of something here. In my IBT, I built my own sort of satellite finder thing. Got one of the boards with the little logarithmic detectors made for cell phone, cell site signal leveling control. And they're very accurate little chips, and they do make a pretty good thing for your IBT. However, I initially just had the thing mounted on the chassis there and thought that was good, connectors going in and whatever. This wideband chip would pick up Wi-Fi signals, cell phone signals, alarm system signals, all kinds of things there. As soon as I put it inside of a metal box and then put the feed-through capacitors on all lines through, it would work great once I sealed the lid of the box. Until the lid of the box is sealed, the feed-through is not doing any good because signals can go around the edge of the box. But once a box is properly sealed and signals brought through with feed-through capacitors, higher frequency stuff is very effectively removed. Now for lower frequency stuff, sometimes a larger conventional capacitor will be hung like from the pin of the capacitor to ground on either the inside or outside, because you do have a limited amount of capacitance here. So for low frequency, but for all the high frequency stuff that was running me nuts, those 3 feed-throughs on the control lines and output line going in there, all of a sudden left it so, no problem at all with interference. The laptop can run next to it. The Wi-Fi doesn't talk in here and a bunch of stuff like that. Then there's the extreme case. I don't know if they're doing any of this at NRAO, but it, I spent some time in the Air Force working on comm nav equipment, and you found that wherever the control signals from the control box went inside of something, you always found there was a double wall box there. You went through a feed-through capacitor, and then there was a small inductor put inside there, and then a second feed-through capacitor. And this was made because you need extreme isolation for military stuff. There was also something that they called Tempest, which I was only briefly exposed to, but it's basically you don't want any of the operational signals inside a box finding their way to the outside world and being detectable at all on the wires by anybody spying or whatever. So this combination here gets used a lot by the military for the extreme isolation. You have a radar transmitter and a very sensitive receiver right next to each other on a plane or a ship. Without the double wall box and the super thing, it just doesn't work. I have yet to see a place where radio telescopes have actually used that, but with as noisy as computers are getting, we may get there where we have to double wall going inside of our RF equipment boxes. Let's take a little look at a DC power line filtering application. In this case, laptop computer dies, the screen gets crushed and it's old enough it's not worth. You got this 19-volt power supply laying around, which is made for the laptop computer. It puts out a reasonably good 19 volts. However you start looking at it, there's a lot of noise on it. Everything in the world uses switching power supplies, and switching power supplies tend to make noise from DC up to blue light. Well, this thing has plenty of watts out to run things like my IBT and other such stuff. The only thing is it's noisy as heck. So I ended up putting a filter network there where capacitors and ferrites were the big part of it. So in this case, I'm going to kind of go through each component. We've got L1, it's what is called a common mode. So any noise where both these lines are trying to move together with the noise is filtered off by that. And I put a ferrite sleeve on there, which is good over very good at very high frequency range out to 1,000 megahertz. Below 20 megahertz, it kind of falls aside. Then for differential mode, put a couple of small ferrites there. And then 100 microfarad electrolytic capacitor, the normally evil guy if you're looking at accuracy or whatever. But here's exactly what they made for. They hold a lot of energy. They level things out and keep care of all of the noise up to about 5 megahertz or so. Above 5 megahertz, the little ceramic caps take it. And you have each side of a choke coil, and the choke coil combination. Now this choke coil would be for the lower frequency noise. So by the time you've went through all of this stuff, you've got a pretty clean power supply here. And then I went through a 12 and a 15 volt regulator because I use both voltages in the IBT because that's how you switch polarization. The 7812 regulator calls for 0.1 capacitors, microfarad on it. The 0.1 microfarad capacitors are put there to make the regulator stable. So those aren't put back here. They're put immediately next to the regulator with the shortest wires possible to ensure the regulator behaves itself. So those want to be within a couple tenths of an inch of the regulator pins to make sure the regulator behaves. Regulators are pretty clean outputs generally and don't need a lot of output capacitance in most applications. By the way, part numbers I put in there, and this is in my paper, the same thing, came from DigiKey. And I just use them because their online catalog for selecting parts, works pretty well for me. Mauser Electronics also has a similar thing. I'm less familiar with their catalog. others out there, the catalog thing isn't as good, so I'll always use one of those too. And then we're going to look at logic ICs. What happens? You got a board full of logic ICs. I mean, this is interesting to the guy that designed the Raspberry Pi or the Arduino boards, you know, and sometimes they aren't interested enough because those boards generally put out a little bit more RF noise than necessary because they didn't do the best job of putting the little capacitors right next to the chips. And with the modern higher speed chips, you actually turn up with a very small capacitor next to each logic chip right at the power pins. And some larger logic chips may have 4 or 5 capacitors, you know, sprinkled around them to get the, you know, desired, you know, effect there of keeping it, you know, the chips working reliably. Like I said, you know, logic chips, registers lose their mind, memory forgets stuff, other such things if the power lines aren't stable. So you'll have 5, 3.3, and cores of some microprocessors are getting down to 1.2 volt or whatever for the inner core. But whatever, the bypass capacitor is critical. Now these will always be ceramics, normally X7Rs, that's where they're applicable. But you'll almost always have a tantalum capacitor on the board somewhere. And tantalum is interesting because they have some series resistance inside of them that's fairly consistent from part to part. And that series resistance actually damps out the oscillations you get because you got a capacitor here, inductance of your power feed traces working together, and you can get a little ringing from that, and that damps out the ringing. So if you replace that with a super quality capacitor with no series resistance, your ringing would build up and you may get an unstable supply. Yeah, this is kind of power supply from past history, so it's probably not too applicable, but you know, an interesting problem I ran into once, gave a design to a draftsman to lay out a circuit board, and the ground point for the regulator was tied right here at the rectifier diodes rather than right at the filter cap. And the result of that was as the pulses from the power line charge the filter cap, you get a voltage drop across here. And this voltage drop would move the ground pin for the regulator, which tells it what it's supposed to regulate its output to. So you turn up with this noise on the output of the regulator, which was actually a couple hundred millivolts due to the you know, poor layout. And all I had to do was cut the filter cap trace from there and put it where it was common with everything else, and things suddenly worked. So for a capacitor to work right, you know, it needs to have good connection to the points that it needs to filter. You know, it can be quite important. Yeah, not much else to say there because nobody's building power supplies anymore in general. Now, this is a case from, you know, a radio receiver that I'm still using, which is an analog receiver. And I'm using a polypropylene capacitor and a resistor to make the integrator stage, and or you know, essentially low pass filter for my data from my detector. This capacitor, I've actually got several of them that can be switched in out. It's a little switches as needed. But there, a polypropylene capacitor is, actually I used a polycarbonate, excuse me. But polypropylene is what you would use now because they quit making polycarbonate. The one factory in Germany that was making polycarbonate film quit, so all suppliers of polycarbonate capacitors went away. Polyester might work fair there, but the polypropylene is much, you know, or polycarbonate are both much better because they don't change value, don't have any dielectric absorption. They're just a pure capacitor. So when you know, integrate something, the result is pretty pure. If you use a tantalum capacitor there, it you know, do pretty bad. An electrolytic, it'd be an absolute joke. A high K ceramic, you know, class 2 ceramic there, you know, be microphonic, you know, vibration from your fan would add to your radio telescope data, for instance. Now, one thing that's interesting that when you get a large capacitance going into a, you know, IC amplifier like that, if you turn the power supply off and the power supply dies quickly, the energy in this capacitor is going to try to go back to the IC and in fact blow it out. The experience speaks. So you have to put a small resistor in series there just so the current available in the capacitor can't get large enough to blow the IC. So that's something I learned from bad experience. You really need a resistor there from that. Most of the time, of course, the integrator function is moved to software in a modern receiver. Okay, most people are just buying little preamp things, but you know, in the past we used to make our own, you know, gas FET preamps and or hemp FETs or the various type of FETs. But the capacitor selection was very critical. The source leads, sometimes some designs actually depend upon having a slight inductance there, so you have to use the same capacitors that the original designer of the preamp used. This capacitor is not too critical. This one needs to make sure there's no RF there. Small resistor to your really big, you know, capacitor there. These two capacitors are critical because any loss in them adds to the you know, noise figure of your preamp. You bought a very expensive FET. Well, now they're $1. They used to be 40 bucks for a good FET. And after paying 40 bucks for a good FET, you don't want to sacrifice any noise figures. So these capacitors and the inductor here also were selected very carefully to have almost no loss. So that's where things like the porcelain capacitors and the you know, air piston trimmers came in. Then there's the stray cat and the stray capacitance. You know, everybody's seen a stray cat show up occasionally, you know. Don't feed it or it's your cat after that point. But anyway, stray capacitance, it also shows up. Yeah, you turn up with a capacitance. You wire insulation, it's an insulator, it's a dielectric. Inside you have copper. So you turn up with capacitance between these wires. And I've seen some real disasters happen from cables. Somebody puts a line to power a compact fluorescent display, yeah, the backlight on it, along with a you know, some logic signals and other power signals, and there was all kinds of garbage coming across. It was all due to the stray capacitance between the wires. Somebody just forgot there was capacitance there. Sometimes there's a thing called the ribbon cable where the wires are glued together in a specific order or make a little ribbon. On those, you can control stray capacitance a lot better because you in your ribbon, you hook every other conductor to your circuit ground, and that can leave you quite good isolation going down a cable. Not quite as good as a shielded cable, but pretty good. And how am I doing for time? Okay. Oops, back up one. Talk about electrolytic capacitor failures. Electrolytics are something that there's some definite ratings on them, and manufacturers of PC motherboards and PC power supplies have not been good about keeping the ratings proper. You can see that capacitor is bulging at the top. This one's got chemicals leaking out. This one's got a bulge, lifted off the board, stuff like that. And more extreme cases, the capacitor goes boom, sounds like a firecracker going off inside your computer or whatever. And there's confetti all over the place with a nasty smelling chemical associated with it. Yeah, so in applying electrolytics, something called ripple current and ESR has to be watched. Fortunately, nobody designed switching power supplies except people that really get into it. You buy a switching power supply and hopefully they did a proper job on selecting that. And of course, I've got my crazy conspiracy theory. When they make the power supplies and the computer motherboards, they purposely undersize the capacitors so that they'll have a slow failure. You know, if you undersize semiconductors, they normally die pretty quick. But you undersize electrolytics, they just kind of gradually get worse and worse. And after 2 years, right after the warranties went out, the capacitors got bad enough that your power supply, you know, had a capacitor go boom or it quit. Electrolytics aren't working right on your motherboard, and the power supply becomes unstable, and the computer starts doing wacko things because the chip's not following its instructions properly. So anyway, little conspiracy theory. It's really the manufacturers trying to assure they wear out in the proper time. Who knows if that's true or not? Maybe it's just trying to make the design as cheap as possible. But anyway, if you ever look at your PC motherboard and see capacitors you know, bulging, it's time to replace it. They're going to go. Same with power supplies. They go, you know. I first got on the thing with power supplies when I was designing a power supply for LED lighting. And the power supply for LED lighting was a big bulky thing. And the salespeople said, why is that thing only 140 watts? It's a lot, twice as big as a PC power supply that's 400 watts, you know. And I had to explain, well, I took a few PC power supplies apart that had died and showed them, well, we don't want this happening to our lighting power supply because we claim it's going to last 10 years with virtually no fallout, almost no failures in 10 years was our goal, versus a PC manufacturer maybe wants it to die at 2 years. I don't know. Our power supply for lighting would go up in an attic, so the outside temperature might be high, no cooling fan, so it'd get pretty hot. So, that was when I started looking at, well, what do they do in PC power supplies? And I found out that I was not impressed with their rating on capacitors, because I reverse engineered a few designs and I'd say, well, I'd never do that. Of course, I'm designing industrial equipment and they're designing for a mass consumer market, a little different of a game. Anyway, oops, back up one. There's a picture of me at work in my lab there. See, I've got my capacitor on a capacitance meter, a little candle and all that, little silliness. And time for questions there.
Well, we got one from Don. You're going to talk about a variac capacitor.
Oh, okay. I had put it in the paper about the varicaps, which they're a semiconductor junction always have some capacitance, and for electronic tuned oscillators, because almost all receivers now, the oscillator is actually a electronically tunable oscillator, and a bunch of digital circuitry measures the frequency and tunes it to a very precise frequency. And so that you're taking advantage of the capacitance of a semiconductor junction. As the voltage goes up, the depletion layer in the semiconductor, the area where there's no charge carriers, becomes larger and larger on a reverse bias semiconductor. So as that distance becomes larger, the capacitance drops. So if they optimize the mix when they're doing the magic of making semiconductor devices for the capacitance, they can turn up with a capacitor that's reasonably low loss, and they can electronically tune it over a range of maybe 3 or 4 to 1 on capacitance, and still have pretty good behavior. So that's how anytime you see something with a phase lock loop, they had a varicap or a voltage variable capacitor, which was actually made with a semiconductor there for that. The other place where variable capacitance of semiconductor junctions has been used is in high power frequency multipliers, and that's falling by the wayside because they've got transistors and things that work at those frequencies. But originally, if you wanted a 4 gigahertz signal source way back, you couldn't get transistors that would work at those frequencies, but you could get a voltage variable capacitor. So basically, they took a voltage variable capacitor made with a specially processed diode, mounted on a big chip that was heat sinkable, and they would drive that with a sine wave, and the capacitance changing across sine wave would generate harmonics, and the harmonics were taken out with tune circuits. And capacitor being a very low device, you could probably get 60% multiplication. So you put in 500 megahertz, you get out 1500 megahertz, and you get 60% of the power by using a voltage variable capacitor. And those have totally fallen by the wayside for any practical application, I believe, because they get semiconductors that work directly as amplifiers and multipliers at such high frequencies. Next. Okay,
Don, you just you left when as soon as he started your variac question, but I hope you got it all. Let's see, from Wendy.
I heard the whole thing. I was just walking around my computer.
Oh, great. Okay. Wendy, excellent presentation information. Bill Miller. Yes, excellent, Bruce. As an ex-power supply engineer, I would say you nailed it. No real conspiracy there that I saw. Electrolytics just dry up and fail after 5 years or so. Peter East, brilliant talk, Bruce. Took me back a few years. Kim Hay, excellent talk. A lot of information. Thank you. Mike, I don't know what have means there, but got to finish this.
Okay, so now everybody is real suspicious of their computer motherboard and computer power supply. And I don't know, I'll go for the conspiracy thing with the manufacturers. It always sounds good having a good conspiracy theory. So be suspicious of your computer. If it starts acting up, pull the cover off, look and see if half of the capacitors on the motherboard have a little bulge in the top. Yeah, well, that motherboard's pretty well toast. Yeah, especially the way they surface mount the capacitors now by robotics. You're not going to change them by hand easily.
Right.
So I had a few pieces of equipment that I just wanted to briefly show what they look like. So I'm going to close my share if I can find the button to do that. Okay, share. Where's close share? All right. I never can find the button for that.
It's in the bottom. Or no, I'm sorry. Yours is at the top. Go to the top of the screen.
Okay.
Yeah.
New share. Okay. Share. No, I don't want a new share. Okay.
I got Preston saying I have a bad computer power supply and one computer that I need to replace. And don't we all, Preston?
Okay, I can't find the on share button. I found the
All right, I can actually do that remotely, I think, here.
Okay, God, I wanted to bring my camera back for a minute here. And
all right, I just unshared you. All right, you try resharing.
Only one?
Okay, I still see my screen there from the sharing.
Yeah, you're unshared now, so if you don't try sharing what you want to share.
Okay, so I closed. Okay, looks like we're back now. Can we get me full screen here?
Yeah, as soon as you share, you'll be full screen again.
I will.
Well, give it a shot.
Share screen. Nope, that brought that up.
All right, I may have undone you here. Let's see. All right, let me try.
I never get along with computers. Maybe that's why I have conspiracy theories about the power supply. I don't get along with them. From making analog equipment in the 70s and everything, the computer is a different approach. I'm the guy that actually has used a slide rule and know what it is. Used it on the job and used the first calculators and actually went back to the slide rule in a lot of cases because if you're getting components where you need to know about the value, the slide rule gives you an almost instant answer, and the calculator gave you an answer to all kinds of digits when you're picking a 5% resistor. But anyway, I'm still not on share. Okay.
Try it again. I just flipped some switches on my side. See if you can do it. Let's see. I got while you're trying to do that from Kim. Good talk for fundamental tutorial at the IEEE EMC Symposium online starting tomorrow. Let's see, from Gary Evans, if manufacturers use electrolytic capacitors of large voltage values, then absolutely needed in the circuit, would they be expected to last longer?
Well, as a matter of fact, yes, they would last longer if you used a higher voltage rating, but that would be kind of a side effect because if you use the higher voltage rating, you've got, of course, more margin on the voltage, but usually it's actually ripple current, the charge and discharge current that kills them. But if you get that voltage rating higher, the capacitor becomes physically larger, and physically larger gives it more surface area to dissipate whatever heat's inside it. And actually in designs I had used where I was expecting them to last 20 years and more in electricity metering, for instance, they want that thing to still be working after 20 years. And use that and you were in good shape there. Okay, I'm going to try my share screen button again, see what happens. Nope, that just put me back there. I'm trying to find the on share screen, but
okay, well, go to share screen and you should show all your screens that you've got open in your computer.
Bruce, you have to have what you want to share open in a window.
There you go. I think he's got it.
Okay, so I got rid of that. Now I can find my, okay, what do I do with that? Yeah, I'm not doing good with Zoom. Well, I was going to show a few items just around the room there, but how are we doing for time? Have I used up my time?
Yeah. No, you've got, you're actually you got 20 minutes because we've been running early. So you got a few minutes to go work this out. And meanwhile, here's the plan, people. I'm going to give him another 5 minutes. Then then Kevin starts at 15 after. So we're gonna all take a quick 10-minute break or so and come back at 15 after as soon as Bruce shows his thing off. Just because I think we need a quick break. Has been talking for a long time here.
Richard?
Yes.
I would like to do a group photo. And what I would like to have before we start the next presentation, everybody, not now, but everybody turn your video on, and then I'll go into full, the screen that shows like Hollywood Squares, and I will save those photos, and that'll give us a group photo of everyone who's on. So if we could do that after before the next presentation, I would appreciate it.
All right. Okay. So how you doing, Bruce?
I totally screwed that thing up. There's last time I did it, I found a little thing on laying around the screen that I hit, and this time I managed to close it all together.
Okay.
I'm not doing well at zooming. Well, on the little picture, you can see my IBT in the background there. And I'm going to show just briefly get a little bitty picture of it. But this is my signal processor that replaces the satellite finder. It's a lot bigger. And, we had the presentation earlier on using analog meters. Well, I had a great big analog meter there so somebody could read it from 3 or 4 feet away. And that's very handy when you're doing relative temperature things with your IBT, having a really big meter so it can be seen a distance off. So anyway, there's that. And 408 megahertz. Well, there, I can get it in the.
You're not sure yet.
There we go.
There you go.
It's got too much light on it there, but
There you go. Stop. That's good.
That was my map of 408 megahertz of about 6 months worth of collecting data of sky flux density and dodging the sun and interference and other such things, and finally got something. And I could have taken 5 minutes and went to JPL's website and got the same map with a little more detail or whatever. Okay, I think that's about it for me for right now. So we want to go for our group photo thing. And
all right. So thank you. Why don't you stop sharing so we can.
Okay, if I still got something sharing here.
Yeah, here. I'll fix that. I got you. Okay,
Oh.
everybody, turn on your video. And we're gonna smile because we're gonna take a group shot. And hopefully we can get everybody who's online, 69 participants right now. We can get them all on the same screen.
Ken Redcap, are you in the room?
I'll text him.
I had to go put a shirt on.
Uh-oh.
Yeah, mighty nice of you.
Well, that's the days of COVID, man.
I stood on his pants on.
Actually, I was in a Zoom meeting the other day. Actually, I think it was our last meeting we had here with the Drake's Lounge. Somebody had their shirt off, but they had overall straps on, and I was ready to having problems.
Somebody wake up David Westman.
Oh, he's there.
Westman. Where are you?
Don't mess with David. He'll walk you to death if you ever try to walk with him. He's fast.
We just got the notice for a tropical storm watch.
You guys are used to Hurricane 5 winds. I'm not sure why even tropical storms even.
What, in Laurel, Maryland? I don't think so.
Oh, Maryland. Oh, okay.
Well, we're having blue skies and sunshine right now. We're between bands in Tampa.
So David Westman, turn on your video. We're going to take the group shot. Kim, I don't know if you can turn your video on. You've got an icon showing.
Jay Westman, how about you?
KR Sarah, that's Ken. Ken, are you there? Are you getting all
I texted
69?
him and he's not responding.
I'm cold.
Dennis, are you getting all 69 people? I don't think I've got 69 people here on the screen.
Well, you have to, it's going to take up 3 shots.
Oh, okay.
That was not an icon. That's the crest of the Royal Manticoran Navy.
I see.
I apologize. I just wanted.
The Queen will be upset with you.
No doubt.
Hey, I've done the hip hip hooray to the Britannica on the way past our ship. So, all right. Tom Jacobs, turn your video on. Well,
actually, I've got the wrong camera up, and I don't know how I changed it.
All right.
So
Well, let's see.
I have to get out of Zoom and come back.
Well, we can, depending on how long you want to wait, we can, once again, let me say this.
Ken's on the way.
Ken's on the way. There he is.
Anyone who has not heard, we are asking everyone to turn your video on so we can take a group picture. We can put them all on, or on, 1, 2, 3, 4, 5, 1, 2, 3, 4. We can put 25 on the screen at a time, and I'll take 3 shots. Donna Halen, are you in? Okay, got it. Brian Tracy, we got it, no problem.
All right. Well,
Van Proy, he won the generator. There's Bill Miller just joined us. Thank you. I got quite a few. John Colt, Audrey and Jack, Fred Kellerman, Alan Ostrander.
Yeah, everybody stay muted.
Yeah, stay muted, but turn your video on, please. It would be very helpful.
Sorry, Wendy. They put your name in.
Okay, I'm going to go ahead and take the first shot here. We're not in any, what time is the next scheduled?
You've got lots of time.
Okay. Well, let's not rush it. I mean, I want to get as many as we can. Okay, I got over 55 active, 2 telephones. Tom says no video. All right, let's just give it another minute. Everyone, if you can hear me, turn your video on. If you have not yet done so, we're trying to take a group picture.
And one hint, when we take the picture, look at your camera, not at the picture of yourself.
Yes, yeah, that's very good, very good. Yeah, that's very good.
I got James Van Pruin. You on?
John Dewsnap. Alan Ostrander. Audrey and Jack. Brian Tracy.
Gary, that didn't help much. I'm sorry. James, you there? James Pruin.
Can I stop smiling now?
No.
No, you got to maintain
I'll tell you
smiling.
when to smile. I'll let you know before we push the button.
Let's see. I got Charles Hill. I got a picture of you, but no live. Jay Wilson, picture, no live. Oh, Preston, yeah, you're live. I just couldn't tell you were so still. Let's see. There you go. There's Jay. And Ethan Waldo, James Dew, Snap, Tom, KT4XN, Audrey and Jack, Brian Tracy. Maybe you guys are all no video people, but Fred Kellerman,
Well, at least we have their names represented.
That's perfect. Yeah, that's a good start.
All right. I know you don't know who's on my screen, so we'll just do this in 3 sections. Let me close my chat window. I don't need that open for this. Ken, sit down. There you go. All right. Microphones off. Everybody turn your audio off to save bandwidth. Tom, save your bandwidth. Stand by. All right, stop smiling. All right, it's going to group 2. Stand by, smile. Stop smiling. Just about there. I do a print screen and then I have to save them. Stand by. And ready, 1, 2, 3. Stand by, stop smiling. Okay, I got them. Thank you all very much.
Yay.
Yay.
Okay, and Bruce, excellent talk. I got so many great comments about that, and personally, I've been rereading your article so many times because I've totally forgot everything about capacitors. So great job on that, and we're gonna take a small break here. Kevin McManus is gonna present his plates membership using mixture models at 15 after. So we got you got about 9 minutes to take a quick break before he starts that.
Okay, Rich, stop recording.
Got it?
And everybody turn your video off for saving band.